Hi everybody, this is John Whitaker for the Probability Graduate Level class, and this is our fourth video lecture. And today we want to look at independence again, where we're talking about more than one event. And then we want to move on to Chapter 2, which will have to do with random variables, and we'll concentrate today on discrete random variables. Later on we'll be talking about continuous random variables, but for today, mostly discrete random variables, what we'll be talking about, and some characteristics of them. So let's go ahead and get started. The first thing I want to tell you is the definition. And what it says the events E1, E2, all the way up to, let's even listen to E3, all the way up to En are independent if independent events. If for any subset, let's say, or subcollection, say E sub 1 prime, E sub 2 prime, all the way up to E sub R prime, from the collection of events E sub 1, E sub 2, E sub 3, all the way up to E sub n. Then we have this. The probability of E sub 1 prime intersect E sub 2 prime intersect E sub 3 prime and so forth all the way up to the intersection of E sub R prime is equal to the probability of E sub 1 prime times the probability of E sub 2 prime times the probability of E sub 3 prime times all the way up to multiplication by the probability of E sub R prime. So that's the definition for independent events. We will now look at an example. Suppose an urn contains 4 balls numbered 1, 2, 3, and 4. So you can distinguish the balls. A ball is selected at random, and I'm going to find these 3 events. So let E sub 1 be the event that you got either the 1 or the 2 balls. E sub 2 be the event that you got the 1 or 3 balls. And E sub 3 be equal to the event that you got the 1 or the 4 ball. The question is, are these events independent or not? Okay. Well, the first thing I'm going to do is note the probability of E sub 1. That's equal to, well, it's the number of ways that E sub 1 can happen over the number of ways anything can happen. So there are 2 ways for which E1 happens. You choose the first ball, you choose the second ball. And the number of ways that anything can happen, number of outcomes in our sample space where we're choosing one ball out of the bag that has 4 balls is 4, so it's 1/2. P of E sub 2, again, is 2 out of 4, which equals to 1/2. And P sub E sub 3, well, that's going to be equal to 1/2 as well. So that's something to note. And what we've got to do to check the independence here is that anytime we take a sub-collection of more than one item here from our collection of E1, E2, and E3 of events, when we intersect them, the probability of intersection equal to the product of their probabilities. Well, let's see. Okay. Well, note the probability of E1 intersect E2. So that's one subcollection, okay? Well, that's really the probability. So what's E1 intersect E2? E1 was the 1 and 2 ball, E2 was the 1 and 3 balls, so their intersection is just the 1 ball. But you got the 1 ball, and that's 1 out of 4. And which does equal to the probability of E1 times, let's say, which equals to 1/2 times 1/2, which equals the probability of E1 times the probability of E2. So far, it could be, the sets could be independent. Also, the probability of E1 intersect E3, that's equal to the probability, so let's see, E1 was the 1 2 ball, E3 was the 1 4 ball. What they have in common is just having 1 ball. That again is 1 4, which equals 1/2 times 1/2, which does equal to the probability of E1 times the probability of E3. Still, they could be independent events. Note the probability of E2 intersect E3. Well, that's the probability. Let's see. E2 was the 1 and 2 ball. E3 was the 1 and 4 ball, so they still have just the 1 ball in common, and that's 1 out of 4. And that again is equal to 1/2 times 1/2, which equals the probability of E2 times the probability of E3. But there's one more subcollection we should look at. Finally, the probability of E1 intersect E2 intersect E3. Well, what's in common between the events E1, E2, and E3? Let's see. E1 was 1 and 2 ball. E2 was the 1 and 3 ball, and E4 was the 1 and 4 ball. And so the only thing they had in common is the 1 ball. So the probability of getting the 1 ball, that's equal to 1/4. We've already seen that. Which does not equal to 1/2 times 1/2 times 1/2, which is what the probability of E1 is, times the probability of E2, times the probability of E3. So, these events are not independent. They're not independent. But they are something E1, E2, and E3 are pairwise independent. So any two of them would be, taken together, would be independent of each other. And that's meaning, more explicitly, for any two events, the probability of their intersection. So even though I'm not writing this down formally as a definition, it is a definition. Intersection. Is equal to the product of the probabilities of each event. Push it on 2. Okay. So that's what it means to be pairwise independent. Which the last example showed. That concludes all the material out of Chapter 1. You'll remember I sent you a link to an older edition of the text that we're using. And so we're moving on to Chapter 2, which has to do with random variables. And this will be a main focus for our class, random variables will be. And so we've learned some things about probability, and now we're going to be talking about random variables, which we'll be talking about probabilities of the random variables having certain properties. So first of all, let's give a definition of what it means to be a random variable. So a random variable is a function x whose domain is the sample space of a random experiment. And whose range is a subset of the real numbers. Well, let's look at some examples. So here's one. So as an example, let's say a coin is tossed. And so someone would say, well, the sample space is either H or T, or heads or tails. And we've defined x of H to be equal to 1 and x of T to be equal to 0. Then x is a random variable. Okay. Let's give another 2 examples of random variables. So, it's a little bit wordy, but here's another example. Suppose a person will arrive at a bus stop sometime between 5 p.m. and 5:30 p.m. Let X indicate the time after 5 p.m. the person arrives at the bus stop. All right, so just as an example of how this X is defined, X of 523.2. So what I'm saying here is this person showed up at the bus stop at 5 o'clock, 23 minutes after 5 o'clock. Well, wait a minute, it's 23.2 minutes after 5 o'clock. And so what the answer here is 23.2 in terms of what X's output, not answer, but what X's output is, because X denotes the time after 5 p.m. when the person shows up. So that's an example of a random variable. Then X is a random variable. Let's look at one more example. Let X count the number of potholes in a 1 mile stretch of a specific road. Then X is a random variable. So you've got different 1 mile sections of this particular road. You say X of that particular 1 mile, how many potholes does it have? It has a numerical value, and so that's a random variable. Okay. And so kind of the random experiment is which 1 mile are you out that you're looking at in the road. Okay, well, these examples of random variables aren't the same type. And so let me define a particular type that we're interested in today. So a discrete random variable is a random variable whose collection of output values is at most countable. So what does countable mean? Countable means that it has the same number of objects, or the same number of elements as the set of natural numbers. So at most countable means that the number of output values for a discrete random variable has got to be less than or equal to the number of natural numbers. Let's review the three examples that we had. Okay. So first of all, the last example we did was the pothole. The pothole example, random variable, where X counted the number of potholes in the street, 1 mile section of a certain street. That is, or has, a discrete random variable. There could be any number of potholes there. Maybe there's a billion within that 1 mile that we're looking at. Maybe there's a trillion. Okay? Go all the way up to forever. And so but the number of potholes is a natural number. Okay? So that is a countable random variable, so it's discrete. The bus stop example is not a discrete random variable. So every possible number between 0 and 30 is a possible output value for that random variable at the time that the person shows up after 5 o'clock, between 5 and 5:30. And remember, we were talking about any instant, okay? So because we're having any instant here, we're not just talking about integers, we're talking about rational and irrational numbers to be output values. So this is not a random variable. And the first example we looked at, the coin example, is an example involving a discrete random variable. Remember, in that coin example, its only output values were 1 and 0. So it is at most countable because there's only 2 output values. All right, we're going to look at another example, and it'll be an example that we'll use throughout today, for us today. So, let's say, suppose a card is selected at random from a well-shuffled deck. So there's 52 outcomes in our sample space, but I'm going to kind of generically define a random variable here. I'm going to say that x of a heart, so I'm just defining x on 13 of the possible cards. Let's say that's equal to -1. X of a black card, so I'm defining x on 26 of the cards. Let's say that's equal to 3, and x of a diamond, let's say that's equal to 2. Then we can note that x is a discrete random variable. Only 3 output values, so it's a discrete random variable. We're going to be using this. Well, one of the things that we want to do in probability is we want to relate chance to something more mathematically concrete. And what we do is we often relate it to calculus type topics. Sorry. And so we're going to get another function involved besides the random variable. And for a discrete random variable, here's what we'll say. Associated to a discrete random variable is a function. We'll call it f of x, called the discrete random variable. Let's give it a name, x, okay? So that's my discrete random variable. Is a function, f of x, called the probability mass function of big X that is given by so here's the definition of the PMF. It's f of x is equal to the probability that big X, the random variable, is equal to x. So the probability mass function is a function associated to a discrete random variable that gives you the chance, so f of little x is equal to the chance that the random variable was equal to that output value little x. So as an example, let us go back to the previous example with the card selection. So card is selected at random from a deck. So everything's equally likely to occur. Define, just as we had before, x of a heart, that was equal to -1. X of a black card, that was equal to 3. And x of a diamond, that was equal to 2. What we want to do is we want to find the PMF, probability mass function. Now the probability mass function is going to be defined on all x values over the whole real line. Okay? So, so my direction is to find the probability mass function and I will abbreviate that. PMF, as I said, of X. All right, so the PMF is defined over the whole real line. And so recall, f of x, that's the PMF, is equal to the probability of big X is equal to little x. All right. Well, wait a second. Let's think about this. What were the output values for x? Well, there were only 3. It was -1, 3, and 2. And if you're not one of those numbers, the probability that x is equal to that number, let's say 17. Probability that x equals to 17, well, that's 0. Because 17 is one of the output values. So a lot of times this function is 0. Most of the time this function is 0. When isn't it 0? Here's what I can do. Note the probability, this is not 0. F of x is not 0. When little x is equal to one of the output values. So what was one of the output values? Well, the smallest one was -1. So what's f of -1? Well, that's the probability that x is equal to -1. Well, that's the same thing. How did x become -1? That means that you were choosing the card, and what you chose was heart. And what's the probability you choose a heart? Well, it's 1/4. So f of -1 is 1/4. Also, f of, let's say 2 Well, that's the probability that x is equal to. Well, when was x equal to 2? X equal to 2 when we got a diamond. So that's the probability that we chose a diamond in our picking of a card. And what's the chance we pick a diamond? Well, that's 1/4. And finally, f of 3, that's the probability x is equal to 3. And that's equal to the probability of getting a black card. And the chance of that happening was 3. So any other number for our PMF's input value would generate 0. So I'm ready to write down this piecewise defined function that is the PMF of our example. So, f of x is equal to, well, it's 1/4 if x, little x, is equal to -1. It was 1/4 if x was equal to 2. It's 1/2 if x is equal to 3, and it's 0 otherwise. And sometimes people won't just list this 0 otherwise, it's just understood. And some characteristics of a PMF is what we want to look at next. And so what we say is let x be a discrete random variable. And f of x be the PMF of x. Then, first thing I want to tell you is that 0 is less than or equal to f of x, which is less than or equal to 1. Why? Because f of x is a probability. That's easy to see. 2, the sum over all x values such that f of x is greater than 0 of f of x, that's got to be equal to 1. So if you sum up all these probabilities, you're going to get 1. Okay? So that's something worth noting. And if you look at the PMF that we have above, I should have said something a little bit more. You could also say where x is an output value of big X, instead of saying where f of x is greater than 0. So just looking at the output values of big X. If you look at this example here, first of all, note that each output value for f of x is in between 0 and 1. 4.4, 1/2, 0. And if you were to sum up for x equal to -1, 2, and 3, what you'd see when you sum up the PMF values, you'd have 1/4, 1/4 that makes 1/2, plus 1/2 that makes 1, and that's what we're trying. So that'll happen every time for a PMF. Those two. Okay. There's another function associated to, well, all random variables, not just discrete ones. So we'll define this generically. So as a definition, associated to a random variable is a function big F of little x called, let's give the random variable name, x, called the cumulative distribution function x that is given by f of x is equal to the probability that big X is equal to little x. I would like to list some properties of the CDF. So some characteristics of the cumulative distribution function. Again, I'll call it the CDF of x. Remember, that's big F of x. So we can think of this either through limits or an extended a function who's defined on extended real numbers. That means it's defined on infinity and minus infinity. And first of all, we say, what's f of minus infinity? Well, that's going to be 0. So the probability that the output value is less than or equal to minus infinity, that's 0 for the random variable. And f of infinity, well, the chance that x is less than or equal to infinity, well, that's 100%, so that's 1. 2. Okay, so a second thing that I'd like to say is that f is non-decreasing. Never goes down. 3. A third thing is that f is right continuous. Indicate what I mean through an example of that. And then a fourth comment that I want to make is that the probability that the random variable is between two numbers, A and B, is equal to f of B minus f of A. So those are the 4 characteristics I want to highlight for cumulative distribution function. Okay. Next thing I want to look at is an example. So let's consider that chord example. Chord is selected from well-shuffled deck. At random. Again, we're going to define x of a heart to be equal to, I think it's -1, x of a black heart to be equal to, I think it's 3, and then x of a diamond, well, that's equal to 2. Now, find the CDF, cumulative distribution function of x. Okay. Remember what that is. That's f of x. The first thing I'm going to do is remember this definition. Well, f of big X, big F of little x is equal to the probability that x is less than or equal to little x. All right. Well, let's note this. What if I ask you, what is f of -2? Well, that would be the probability that x is less than or equal to -2. Well, let's look at the output values for x. They're -1, 3, and 2. What's the chance that x is going to be less than or equal to -2? Well, it's 0. Why is it 0? Well, there's no chance that it's less than or equal to minus 2 the output value for x. Because output values for x are minus 1, 3, and 2. So they're always, output values are always bigger than minus 2. Okay? It can't be less than or equal to minus 2. That's 0. So that makes me think that really the first place where we're going to have a non-zero answer for the cumulative distribution function is when we look at f of minus 1. So what is f of minus 1? That's the probability that x is less than or equal to minus 1. Well, what's that? Well, that's the probability that x is equal to minus 1. Same thing, because of the output value possibilities for big X. Well, that's the same thing as the probability of getting a heart, and so that's 1/4. Well, let me ask this. What's the probability, what's f of, let's say, 1? Well, that's still the probability that x is less than or equal to 1. Now, look at the output value. What output values are less than or equal to 1? Well, it's still minus 1, so that's the probability x is equal to minus 1. And so that's the probability that we got a heart. That's still 1/4. Wait a minute. When's the next time we're going to have a change? So it was constant here between minus 1 to 1 for a big F. When we're going to have a change when the input value seems to be for a big F, an output value for a big X. So let's say, what about f of 2? Well, that's the probability that x is less than or equal to 2. That's the probability, well, when can x be less than or equal to 2? It happens when x is equal to minus 1 or x is equal to 2. Now these are, if you will, mutually exclusive events. They can't happen at the same time because they're the probability of a heart or diamond. And, well, the probability you got a heart or a diamond means you got a red card, that's 1/2. And then, you know, if you look at f of 2.5, that again is going to be 1/2. So the next time we're going to have a change in the CDF is when we look at f of 3. And that's the probability that x is less than or equal to 3. Well, that's the probability that x is equal to minus 1 or x equals to 2 or x equals to 3, and that's equal to the probability of a heart or diamond or black card. Well, that's the only choice you can have. That's 1. Yeah, the chance that the output value is less than or equal to 3, well, all the output values are less than or equal to 3, so it's 100%, so that's the 1. So let me pictorially graph this, because remember, maybe I hadn't said this very clearly, that the CDF is defined over the whole real line. So here's the way we can list it. So, thus, the CDF of x is, so graphically, here's the way I can describe it. Look, up to minus 1, we get 0. Then at minus 1, we get a 4. And then it continues to be a 4 all the way up to 2. But at 2, we jump. We jump to a 1/2. And we stay at a 1/2 up to 3. And then after 3, we jump up to 1, and we remain at 1 throughout. So that's the CDF. You could write it this way. It's 0 if x is less than minus 1. It's a 1/2, so it's a piecewise function. If x is between minus 1, here, this should be little x, made a mistake, is less than 2. That's 1/4. It's 1/2 if you're between 2, inclusive with the 2, up to 3. And then it's 1 if x is greater than, little x now, is greater than or equal to 3. That's what we have. That's what it's describing. And just very quickly, first of all, you go all the way to minus infinity, f of x 0. All the way to positive infinity, f of x 1. It's non-decreasing. It's never going down as you read from left to right. Never go down. What we mean by right continuous is this is the last part of the characteristic I'll talk about, is that if you come in to the right of a point, so let's say minus 1, the limit from the right equals to the function value at that point. So if I come in from the right, the limit of big F of x, as I come into the right of minus 1, is 1/4, and F of minus 1 is 1/4. So that's what we mean by right continuous. All right, we've got just a little bit more to cover. I want to go back to specifically talking about discrete random variables. Now, I did a CDF for a discrete random variable. You can have a CDF for non-discrete as well. But we'll look at that type later. Right now, for specifically for discrete random variables, and exactly for other types of random variables too, is something called expected value. That's what we're going to do next. So as a definition, and this is what we'll conclude with, is this topic, definition example. Definition. So the expected value of a discrete random variable give it a name, x, is denoted by e, or expected value, of x, and given by, so e of x is equal to the sum over all little x output values. So I'll say x such that f of x is greater than 0. Of x times little f of x, where little f of x is the probability mass function, the PMF, of the random variable x. So that's its definition. Okay, I'm going to make some comments. Oh, yeah. So, the expected value is also known as the mean of the random variable and is the average of the output values of the random variable. So let's look at an example. Let's go back to that card selection. So a card is selected from a well-shuffled deck. At random. Defined. X of a heart, I think I can remember what that was, minus 1, x of a black card, that was 3, and finally x of a diamond, oh yeah, that's equal to 2. So find the expected value of x. Okay, so this is a discrete random variable. I got a definition for it. Note e of x, well, that's equal to the sum over the output value. So let me write it generically. It's x such that f of x is greater than 0 of x times f of x. Okay, so for us, let's just talk about the output values from big X. That's what we're summing over. That's x equaling to -1 or 2 or 3 of x times f of x, where f of x is the PMF. We calculated the PMF earlier for those particular x values. So let's see, it is, let me write this out carefully. So it's -1 times f of -1 plus it's 2 times f of 2 plus 3 times f of 3. Well, that's equal to -1. What is f of -1? That was the chance that x was equal to -1. That's the chance we got a heart. That's 1/4. Plus, it's 2 times f of 2. That's the chance we got a diamond. That's 1/4. And then plus 3 times f of 3. That's the chance we got a black heart. That's 1/2. Or 2/4. And so here, this is -1/4. This is 2/4. That's 1/4. Here's 6/4. We end up getting 7/4. So a little under 2 is the expected value of x. Now, 7/4 isn't an output value. It's just its average. Okay? You've got 2 exams. You make 100 on one. You make 50 on another. Its average is 75. You do make 75 on any of the exams, but that's what the average is. That's what. Well, I kind of told a story. Let me write this down as a definition. The story that I said was we were going to quit after I did this example. But really, we're going to extend it by one more definition and example. And we're going to extend it. So we're going to say, let x be a discrete random variable. And g of x be a function of x. Then, the expected value of g of x denoted by, okay. So denoted by the expected value of g of x is given by, use this definition. The expected value of g of x is equal to, so we're talking about discrete random variable, is the sum over all x's, such that f of x is greater than 0, of g of x times f of x, where again, what's f of x? Is the PMF of x. Okay, let's look at one example, and then we'll call it quits. So, example, you're not going to believe this. It's the card example. A card is selected from a standard deck. I mean, it's the same example, okay? We're going to let x of the heart, let's say it's -1, x of the diamond, x of the black card, that's what we find next. So that's going to be equal to 3, and x of a diamond, that was going to be equal to 2. And so here, what I want to find, let me write down specifically what I had done as an example. So we want to find the expected value of the quantity x squared minus 2x. So our g of x here is x squared minus 2x. That's what we're trying to find the expected value of. The g is the function of the random variable x. So we just use the formula that's listed top of that board there, where the camera still is. So here, the expected value of x squared minus 2x is equal to the sum over the x such that f of x is greater than 0 of g of x times f of x. What that is the sum as x is equal to minus 1, 2, or 3 of it was x squared minus 2x times f of x. Let's see what that is. That's equal to minus 1 to b squared minus 2 times minus 1 times f of minus 1 plus, well, I'll extend it down here. It would be 2 squared minus 2 times 2 times f of 2 plus, that's what sum means, it's 3 squared minus 2 times 3 times f of 2. Okay, so let's see. This guy is 1 plus 2, so it's 3 times f of minus 1 is 1/4. Plus this part right here is 4 minus 4, that's 0 times 1/4. Plus this is 9 minus 6, that's 3 times, this was 1/2, which is 2/4. So we end up getting 6/4, 9/4, that's our answer. So the expected value of the x squared minus 2x for this particular random variable x is 9/4. Ladies and gentlemen, that's enough for today. Thank you very much for your time and patience.